Okay, ladies and gentlemen, today as we begin talking about ideal gas mixtures, I want to go back and talk about a couple other situations that we've dealt with this semester and how that can correspond to what we're going to do here with ideal gas mixtures. Let's consider a situation where we had a tank, and this tank was filled with water or something, and we put inside of that tank a piece of metal. When we worked on our first law, it was going to be delta KE plus delta PE plus delta U is equal to Q minus W. Now, let's not worry about the Q minus W here. There's not going to be any heat transfer or work here if we say this is a really big tank, that there's a quenching that happens. The metal is going to give heat to that water. Water is going to heat up a little bit. There's no kinetic or potential energy here. We have delta U. And what do we do with the delta U here? Well, we have to look and say our system, if I make our system just this outline here, our system's going to have two items inside of it. It's going to have liquid water, and it's going to have metal. And so when we do this problem, we're going to have to say the delta U of the metal plus the delta U of the water is equal to 0. And we do that because the properties change differently in the metal than they do in the water. And we do this through the incompressible substance model. Okay? No problem. No problem at all. Okay, so here's what I did. On the third exam. The third exam. Time's flying by so fast. I gave you a problem that had a very similar idea. Now we have this piston cylinder, movable cylinder and piston in the middle, and I had section 1 and I had section 2. And now we don't have two different materials, but we have air in both 1 and 2. And I had hinted to you by the way I presented the problem is that there was a control volume here, and I wanted to find out what the equilibrium temperature is. Well, this problem is the same as this problem here. We have two different materials. Now they happen to both be air, and that's what maybe confused some of you or confuses some of you. They're both air, but they're starting at different places. So if we were to look at this, if we were to get down to that question, we were to have delta U is equal to Q, because there was some heat transfer in this problem, right? There's some heat transfer in this problem. Well, the delta U, I can't just write this as mass times U2 minus U1, because my U1, my internal energy at state 1, is different for both of these. It's different for both of these, so I have to write mass of 1 times U2 minus U1 of 1 plus mass of 2 times U2 minus U1 of 2 is equal to the heat transfer. Okay, now, this is fundamental to what I try to get accomplished in my thermo classes. And I'm learning some things this summer about remotely teaching you. I don't get to see when your face is scrumpled, that's the word. When you have a question in class, I don't see if I make a mistake in the lecture or I'm going too fast in a lecture that you want me to slow down. I don't get to hear, stop by my office and say, Dr. Wakeland, I don't get that. There's that piece that's missing, but that's what we have. That's where we're at. That's what we have to figure out. But fundamentally, I want to make sure that you understand the material and you don't just try to regurgitate it through some sort of memorized form. Okay? I was hoping that if you saw this problem, that you would say, hey, I can't look at this just as air. I have to look at this as air in two different forms. One's a hotter air than the other air, and they're going to go from, one's going to go from hot and one's going to go from cold, and they're going to meet in the middle at some equilibrium temperature. Okay, that's what I was hoping for. Now, I haven't necessarily graded all the things. In fact, I should say haven't necessarily. I have just looked over a couple of them, and some of you just missed the mark. And that's disappointing for me, and that's disappointing for you, and I have to say that is, not everything is on you. Some of it's on me, where we're going to go with this. But I need you to understand this idea that if you have two different things inside your control volume, even if they're the same material, but they're starting at different points, that you have to treat them as two different paths, two different delta U's. Okay, you can't treat it as one. You can't treat it as one. Now, why am I bringing all of this up? Because what we're going to be doing now in chapter 12 is we're dealing with mixtures of all different types of gases. Okay? And so we're going to have to look when we have our equation delta U is equal to Q minus W. Well, this is going to be the total delta U. And what's that going to be equal to? The sum of all the little delta U's of every different substance that we're adding up. Just like we did with metal and water, just like we did on that third exam. That's what we're looking at. So I want to link this back. It's not new. We're going to talk about some new ideas, some new ways to go about it, but it's not a new a new concept that we've been working on or developing right now. This is something that we've done before. Okay, so let's talk about enthalpy, internal energy, and entropy, and specific heats for ideal gas mixtures. Okay, so for any system we can work on this. We might say that the internal energy total is equal to the internal energy of substance 1 plus the internal energy of substance 2 plus the internal energy of substance 3, and I should make sure this is the big U's, plus dot dot dot, plus the internal energy of substance J. So we just have to add up from I is equal to 1 to J of all of the internal energies of every component. Okay. Same thing here. The enthalpy total is equal to the summation of the enthalpy of every component. I is equal to 1 to J. Okay. Nothing different about that, just adding up all the different internal energies. Now, let's look about this is on a mass basis, right? This is on a total basis, okay? Let's look at what would happen on a molar basis. Okay, now we're going to be talking about number of moles. Okay, what way we could do this is we could say, well, the total internal energy is equal to the number of moles total times U bar total. Now, what am I putting a bar there? I'm putting a bar because whenever I put a bar over something, I know it's on a molar basis. Basis meaning the denominator is going to be per unit mole. It's going to be internal energy per unit mole. Okay, and I'm taking the total number of moles times the internal energy of the substance, the total substance. Or I can write this as N1 U bar 1 plus N2 U bar 2 plus N3 U bar 3 plus dot 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 Nj U bar j. Okay, so we're just basically here adding up from I is equal to 1 to j of Ni Ui. Same thing can be done with enthalpy. So I'm not going to just go and repeat those. Same thing go for entropy. I'm not going to repeat those things. Okay. Now, what happens if you do it on a mass basis? Okay. The internal energy total, which is the same, it's going to have units of kilojoules, is going to be equal to the mass total times the internal energy total. Now I don't have to put a bar there because we're dealing with things in a mass basis. Okay, this is going to be equal to mass 1 U1 plus mass 2 U2 plus mass 3 U3 plus dot 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 plus mass J times Uj. Summation of I is equal to 1 to J of the mass of the component times the internal energy of the component. Okay, nothing different. They're both going to give us the same answer of internal energy. We try to see what's our perspective. Are we looking at it from a molar basis, or are we looking at it from a mass basis? Okay, same number here. Now, if we take this equation here and we divide by the number of moles total, we get that the internal energy on a unit mole basis is going to be equal to I is equal to 1 to j of the mole fraction of the component times the total internal energy. And that makes sense. You have this much internal energy. Let's say it's 500 kilojoules per kilomole. Well, you only have 20% of that. So you take 20% of that total. Okay? 20% of the total is what you deal with. So you're going to add that up and say, well, I have 20% comes from here, and 30% comes from here, and 50% comes from someplace else. And that all adds up to be what is the internal energy of that mixture. The same thing happens here. If I divide this by the mass total, I can get that the internal energy is equal to the summation of I is equal to 1 to j of the mass fraction of each component times the internal energy of each component. Okay, so we're adding up each one of them. We're taking what fraction we have there and taking it times that substance's internal energy. Okay, these are important but straightforward. Well, I shouldn't say straightforward, because sometimes they can get complicated, because what happens is I can show you a problem. We can do it 5 or 6 different ways. We can do it 5 or 6 different ways with this subject, and so I'll talk to you about that in a future lecture. Okay, let's stop right here, and we'll move on to our next segment.